Alright, time for another draftphysics.com, debatephysics.com also, but no debate possible. Can't find anyone interested in defending the classic physical model, or whatever, the popular model of physics, because that's all it really is a popularity contest. And that's all you wish from your civilization, is to hear whatever the popular opinion is. What's the lowest common denominator, stupid ass butthole fucking theory there is? Yeah, tell me that all the time. Shove that in my face constantly. Because I can't do any thinking for myself. Yeah. So, anyway, yes, I'm insulting you. It's just pathetic. This is the world we exist in. You be so goddamn fucking stupid. Sadly. And all right, so anyway, wait. It's just such a. This is almost a no-brainer kind of subject. So I don't know even where. I mean, let's begin with the beginning, right? This is the obvious statement. Okay, this is the scale problem. So their understanding is that okay, this has a mass. It's an object with atoms and a density. And the fact is gravity is pushing on it right now, and that pushing force is going through me into the ground. And I can see the pushing force better if I put it on a scale, because the scale has the disadvantage of, well, the first act, happens, and then the second act is pushing back, and there's always another first act. The first act is a constant, and so it will read on the scale, okay, the pressure that this is creating by actually moving into the earth. It's measuring the movement into the earth, okay, the weight, the pressure. All right, and the simple truth is that this is what physics says. That's 1 unit of energy, okay, that much pressure, that much pushing. It's an amount of push, okay, energy. And they say that this, okay, just doing exactly the same act, now I have 4 units of energy in this spring. Now it's only compressed twice as much, obviously, but they say there's 4 units of energy in there. And if I could just keep doing silly things like this, right? Just to make they say, okay, there's 1 unit of energy, and now I have 2 of these, and I slide the 2 on. Now I have 9 units of energy. That's their physics. That's what all these naysayers and nitpickers and rejectionists, okay, all these people insulting my intelligence, insulting yours, frankly, with empty comments and statements about how wrong I am. That's what you people are defending, okay? Something that illogical. All right, and Wikipedia doesn't want to hear the argument, of course. Now, I guess I'm going to propose that maybe someone in the audience, if you want to email me, if you're willing to create an account at Wikipedia called maybe the Ghost of Draft Science, and we'll just see if we can get them to respond to any arguments ever. And yes, you'll have to take the risk that you'll get blocked by the Wikipedia, and you won't be able to be an editor in the future. You're probably not sacrificing much. But anyway, so anyone interested in, and I'll just give you the simple little paragraph arguments about why this stuff is wrong, and you can see how they react, and we'll just see what the panicked reaction is, because somebody's going to point out that the stuff they have on these pages is garbage, okay, and it's garbage. All right, so that should be the Wikipedia page. So, okay, so with the context of the simple argument is that obviously weight is just momentum. That's it. It's nothing else. It's just another way of saying momentum. Weight is just another way of saying pressure, which is the only way you can create pressure is to have a mass moving. So it's pressure, it's weight, it's momentum. So the word that should be used is momentum. Okay, you're just okay, finding out how much momentum something has when you put it on a scale. It doesn't move unless it's in gravity. If it's not in gravity, it doesn't weigh anything. It doesn't have any momentum, right? So if there's no force pushing it, okay, a constant force, then it runs out of force, and that's an impulse. So an impulse is momentum where there's no accelerating constant force. So when you have velocity and you're moving in space and you hit something and there's nothing, you have no engines on, well then yeah, you're just going to give away whatever energy you have to the thing you hit. And so it's going to consume your energy. So the scale will consume it, impulse, and then it doesn't have any more energy and the scale will just push it back up again because it will become just a mass to be moved by the pressure of the spring. Anyway, all right, so in science and engineering, the weight of an object is the force acting on the object due to acceleration. So acceleration is any acceleration, right? And we're really just saying, shouldn't they say acting on the object due to velocity, right? You don't have to be accelerating, you just have to be moving to have momentum or weight. That's it. You just have to be moving. You don't have to be accelerated. Okay. Or gravity. So it doesn't, it's just not making this clear distinction that gravity is just a mechanism that gives things velocity. That's all it is. It's a force. It gives something a velocity. All velocities are the same. So again, if I turn the scale sideways, it's going to do exactly the same thing. Okay. So I've how many times do I have to point this stuff out? I mean, this is real physics, and you people just don't give a damn. I mean, it's so. I just didn't think the world was just full of morons. I really thought there were some people that could use their brain and think. They had some logic skills. So I put this weight on here. It compresses the spring a certain amount. Now I can find out exactly how much momentum that is because the spring, generally speaking, gives it back. So if I just lock that position, turn it sideways, it will launch the object at exactly we would say it will conserve a substantial amount of the momentum, depending on how perfect this mechanism is. And I'll get a velocity back. And that velocity is basically telling you what your momentum in gravity was. You had a momentum, and it's going to give it back. So if I put a mouse on the scale and then turn it sideways, the mouse will fly off at the same speed as if I put an elephant on the scale and then I turn it and the elephant. It'll be exactly the same speed because it was exactly the same force that pushed them into the scale. Okay, and that's a really big part of understanding the mechanism, understanding the physics, is understanding it's that simple. A force, a velocity caused the deviation in the scale. Technically, you had a velocity, and you can get the velocity back. And so if you really do play around with that, okay, the general figure is that if I want to double your weight, I raise you 1 centimeter. So if you weigh 10 pounds, I put you up 1 centimeter, and then I drop you, you're going to weigh 20 pounds. So essentially 1 centimeter is 4 times no height, you could argue. But if I go 4 centimeters, I'll double it again. And then if I go 16 centimeters, I'll double it again. All right. So back to the page, right? We're still got that here. Yes. All right. So this page is so mushy that you're almost saying, why did they bother even writing it? It's so pointless. Some standard textbooks define weight as a vector quantity. Okay, some do that. The gravitational force acting on the object. So obviously that's what weight is the gravitational force acting on the object, giving the object motion, which causes the object to deflect the scale. The scale moves. Scales can't move if there's nothing moving them. So it's not invisible something that's moving the scale. Well, it is invisible gravity, but okay. Others define weight as a scalar quantity, meaning what? It obviously moves the scale, okay, in one direction. So why would you call it a scalar quantity when it's clearly got a direction? All right, the magnitude of the gravitational force. So, what is this gibberish? So this is how they begin the conversation about the simple concept of momentum and weight and pressure. Yet others define it as the magnitude of the reaction force exerted on the body by the mechanisms that counteract the effects of gravity. Well, obviously without the stopping force, you can't measure anything. So yeah, you'd be in tough shape. And clearly, some part of that is true in the sense that you will regain an equilibrium on the scale. But the fact is, the equilibrium, okay, has a change in the spring. The spring has stored some portion of your energy. So a portion of the energy that you're injecting, right? And it's not all the energy. It's not adding up, right? So I mean, the simple truth is let's say this is gravity causes something to have energy because it's applying a force every second, it's pushing on something. Well, clearly the scale isn't adding it up. I could sit here with the scale for 10 years and the scale's not going to add up the energy. It's not going to add up the gravitational force. I only get the one shot at it, okay, one unit of it, and that's it. And again, that's because the force down was the first force. That's what it's reading. It's reading the first force because all the rest are reaction forces. So it's always one ahead. All right, you could argue. All right, let's see. The weight is the quantity that is measured for, by example, a spring scale. Now, the other one that's interesting is you can use the lever as a balance, and so you can put a mass on one side and a mass on the other side, and it will tell you what is equal. Okay, so 1 kilogram will always equal 1 kilogram. So the neat thing is you go on the moon and 1 kilogram equals 1 kilogram. There won't be any change. So the advantage of the lever scale is no matter where you go in the universe, it's going to tell you the relative difference between two masses. It'll always get that right. It doesn't matter how strong or weak the gravity is, because it's making a direct comparison between a known weight and the weight you're testing, for example. Thus, in a state of free fall, the weight would be zero. So we know you don't have zero weight. So that's like saying a football player's running down the field at, 15 miles an hour, and he has no weight, in the sense that he's not going to apply a momentum. He has no momentum. It's the same thing as saying that. So free fall doesn't mean you don't have any momentum. It doesn't mean that you're not acquiring force or energy. Because you feel nothing doesn't mean that you're not doing something. So again, the football player runs down the field. He's not feeling himself moving, okay, because all the pieces are moving the same. They all caught up. His nose doesn't, he's not feeling more pressure on one part of his face or on his body than some other part. And the only pressure he's feeling is obviously gravity is still pushing him into the ground. So the only resistance he's feeling is the ground. All right. So it's like, even treadmills aren't a good example, but you really can't get out of gravity for us. All right. But there's nothing zero about it, okay? It's just a velocity, period. And the point is you have a velocity when you're standing still on Earth. When you're just standing on Earth, you clearly do have a velocity. You're creating a momentum and a pressure into the ground. In this sense of weight, terrestrial objects can be weightless. So again, they're obviously not weightless. You can never be weightless if you're in gravity, because the gravity is a constant force pushing you, and it's going to cause you to have a constant force to push on other things. So it's kind of silly to call it weightless. And again, weight is just momentum, all right? It isn't a quantity innately. It's about mass and velocity. You have to have the velocity. If you don't have a velocity, you can't weigh anything. You can't apply any momentum or any pressure. So if one ignores air resistance, one could say that the legendary apple falling from the tree on its way to meet the ground near Isaac Newton was weightless. So again, it obviously wasn't massless, and it clearly had momentum. So why call it weightless? So weightless is just a way of describing a feeling. It's not a way of describing what a thing has. Again, you wouldn't say the bullet is weightless. You just wouldn't say it. The speeding bullet is not weightless. Okay, it has a tremendous capacity to apply pressure for its mass. All right, clearly it's just momentum, and the recoiling gun has the same momentum, obviously the same energy. So it's just so bad, the way they just mess up such simple concepts and just destroy them. All right. The unit of measurement for weight is is that of force, which is the International System of Units, SI, is the Newton. So again, this is all very funny in a sense, right? Because we know that weight is just a comparison, is simple enough. And we've just standardized it to gravity. So we've basically said a kilogram is 9.81 newtons. And so therefore, okay, you can convert that into joules or some other thing and just say, okay, if I want 1 newton, I know it's 100 grams. So the weight of 100 grams is a newton. And then I can go from there and create any other kind of nonsense measuring mechanism. For example, an object with a mass of 1 kilogram has a weight of 9.8 newtons on the surface of the Earth. So just an arbitrary establishment of a standard based on what we put on the scale. And we say, okay, that's the reaction, that's what we'll call it, that's the one we'll use, and everything else will be decided based on those numbers. And about 1/6 as much on the moon. Although weight and mass are scientifically distinct quantities, so I mean, obviously they're not just scientifically distinct, they are actually distinct, okay? It's not about a science. An object that's moving has momentum, an object that isn't doesn't. The terms are often confused with each other in everyday use. Yes, you have a mass, and when you have a mass and a velocity, you have momentum. All right. Comparing the converting force weight in pounds to mass in kilograms and vice versa. So yes, everyday use gets ruined because they have 17 million ways of describing what energy is. Force, pressure, they have watts and calories and all kinds of different nonsense. Further complications in elucidating the various concepts of weight have to do with the theory of relativity. So why in the third paragraph would you bring up relativity? I mean, it really doesn't have anything to do with any real or real world concepts of weight, any kind of mass increase, if it actually took place, which I say it doesn't, wouldn't take place until you're going, 98% the speed of light. I mean, it's just such crap. According to which gravity is modeled as a consequence of a curvature of space-time. In the teaching community, so they have a community. What is that, in the teaching community? When did Wikipedia survey the teaching community? When did it go to the teaching community meeting and find out what the teaching community says? I mean, see, they just make this crap up. A considerable debate has existed over half a century about how to define weight to their students. I mean, you define it as what it is, a mass and a velocity. Without the velocity, you don't weigh anything. With a velocity, you do weigh something in the direction of your velocity. And you only weigh it when you actually hit the scale. You can't weigh it until it actually hits something to weigh it with. You're not going to detect the weight until you make it exchange the momentum. You have to exchange the momentum to measure the momentum. The current situation is that a multiple set of concepts coexist and find use in their various contexts. So they can just make up any truth they want depending on what they're trying to say at a particular time. So they're basically saying weight isn't elemental, weight isn't fundamental, there's no truth regarding weight, you just make up whatever you want. I mean, it's just really, really disgusting. All right, we're not going to bother with Aristotle again and all this kind of crap. Waste of time. It really is a waste of time, right? Yeah, it's a waste of time. Okay, so then we'll talk about maybe a little bit of Galileo in here. The rise of the Copernican view of the world. So this is the simple idea that there's 3 dimensions of space. So apparently that's some sort of challenging notion. Forward, back, left, right, up, down. Oh, no, we can't have any of that. Okay, led to the resurgence of a Platonic idea, like objects attract, but in the context of heavy bodies. Like objects attract, but in the context of heavy bodies. So, again, what they thought the force of gravity, and how, Newton made it clear that the apple is doing exactly what the moon is doing. Okay, it's the same force that makes the apple move, makes the moon move. That's the real story. And it's obviously a force. Okay, and it has simple little rules about its strength and magnitude at different distances. And it's really not complicated at all. In the 17th century, Galileo made significant advances in the concept of weight. He proposed a way of measuring the difference between the weights of moving objects and an object at rest. So again, what's the complication, right? You already know the spring works pretty good. A stick bends, that can work. Lots of things can work. It's just making your measuring device more precise. Ultimately, he concluded weight was proportionate to the amount of matter of an object. Clearly, it's proportionate, but velocity is usually the variable. So you're going to weigh what your motion, your speed is. So the longer you're free falling, the more you're going to weigh. The less free fall you do, the less you're going to weigh, because it's the less velocity you've collected. So, okay, not the speed or motion as supposed by Aristotelian view of physics. So again, they're just talking about the difference between free fall, acquiring momentum, and measuring momentum. So when you hit the earth, you're measuring your momentum. When you step on the scale, you're imposing on the scale, and it's measuring the differential between the earth's pressure and the what it will do. It's rebounding to everything you're doing, but it's one unit of energy behind. So there's one unit of gravity you have collected that it hasn't rebounded to yet. It's always one behind. You step first, it reacts. You step first, it reacts. So you're always one behind. Okay, the rise of the Copernican... Oh, I already did that. Okay, Newton. The introduction of Newton's laws of motion and the development of Newton's laws of universal gravitation led to considerable further development in the concept of weight. I mean, how can you further develop something so simple? That mass moving applies pressure. And so obviously we must be moving in gravity because we can apply pressure. All right, weight becomes fundamentally separate from mass. And you can't fundamentally separate, and I don't think Newton's fundamentally separated it, but whatever. Mass was identified as a fundamental property of objects' connection to their inertia, while weight became identified as the force of gravity. So again, obviously any force can create motion and cause you to move the scale exactly the same way. So I can weigh 1 pound this way, or I can turn the scale and I can weigh 1 pound this way. I just have to apply a constant force to my mass and I'll weigh exactly the same amount. So if I apply a constant force of 10 miles per hour, 10 meters per second this way, I'll weigh the same thing on the scale. Because the scale will do the same thing, really. It'll just push the earth. Okay. All right. I mean, like a wind. You could measure the pressure of the wind. You could put up on a sail, and you can measure how much the wind is blowing. And so you could have a wind that's blowing 10 meters per second, and it will weigh, it'll push on the scale just as much as something, a real weight put on the scale. All right, in particular, Newton considered weight to be, well, wait, did I finish that? Okay, while weight became identified with a force of gravity on an object and therefore dependent on the context of the object. So again, they want to make something so simple complicated. It's just mass and velocity. That's your weight. In particular, Newton considered weight to be relative to another object causing the gravitational pull, i.e. the weight of the Earth towards the sun. So this sentence, sorry. In particular, Newton considered weight to be relative to another object causing the gravitational pull, the weight of the Earth towards the sun. But again, you can use weight to determine mass because you can know velocity, and then you can, and then you can discern what's the missing piece, okay, to its momentum, because it's always going to be a momentum equation. It's always going to be about a mass moving. There's no There's no capacity to create weight if you don't have motion. Newton considered time and space to be absolute, which was really quite, you're saying, gee, he's the only one in the history of mankind. I mean, they say there were a lot of Newtonians, so maybe there was a few back then. But now, currently, there's none. Okay, so nobody understands that space is just 3 dimensions of positions. There's just 3 dimensions of distance between points in space, and that's all there is. There's nothing else. None of you can understand that? Yeah, okay. This allowed him to consider concepts as true positions and true velocity. Yes, obviously, if something moves from point A to point B in space, the point A and the point B are never changing. It doesn't matter where you go in the universe, doesn't matter how you look at it. Point A and point B do not change their positions. And if something travels that distance in a certain amount of time, it doesn't matter where you are and how you look at it, it's always going to be the same time. Newton also recognized that weight is measured by the action of weighing. Okay, so that's pretty, obviously, and it's the same for measuring momentum. So again, if I want to measure the weight of a football player running, I just have him crash into the scale, and he'll do the same thing that we do when we measure something's weight in gravity, as affected by environmental factors such as buoyancy. So we know that all of that, we're taking the atmosphere out of these simple equations. So this isn't about buoyancy. Buoyancy just has to do with the fact that the density of materials, means that they're going to be affected disproportionately compared to each other. Their internal, the pressure they create against each other will be differential, and therefore lighter ones will be ejected by heavier ones, you could argue. He considered this a false weight induced by imperfect measurement conditions, for which he introduced the term apparent weight as compared to true weight defined by gravity. So again, it's just too silly. We all understand that there's air resistance, all these little things that suck up some of the energy, so it's not a big deal. I mean, again, we can all figure out it's just momentum. Okay, although Newtonian physics made a clear distinction between weight and mass, and there's no distinction except for the fact that the mass must have velocity. That's it. That's weight. Weight is giving mass velocity. It's giving it momentum. The term weight continued to be commonly used when people meant mass. So again, it should be clear that the two things are different. Momentum is different than mass. Okay. Momentum means that your mass is moving. All right, this led the moving relative. Okay, it's always your catching device is also moving. So obviously, if your scale is moving away from the object you're trying to measure, then obviously it's not going to weigh as much. This led the third general conference on weights and measures. So all of this technical talk about and you're not explaining what the concept is here at all. Okay. In 1901, to officially declare, the word weight denotes a quantity of the same nature as force. So that's clearly reiterating Newton's claim that momentum and force are the same thing. So it's saying it right there. The word weight denotes a quantity of the same nature as a force. All right, so you couldn't have another reiteration. So this is 1901. Somehow physics knew that weight and force were the same thing, and that means that momentum and force are the same thing. But somehow now they don't know that. The weight of a body is the product of its mass and its acceleration due to gravity. Its acceleration due to anything will create exactly the same phenomenon. So it doesn't matter what accelerates you. The fact is, if you have a certain amount of mass and velocity, you will weigh a certain amount. Okay. Whatever your mass and velocity are, multiplied times each other, will tell you how much the spring is deflected. This distinguished it from mass for official uses. So again, the distinction is meaningless. It's like separating velocity from momentum. How can you separate velocity from momentum? You can't have momentum without the velocity. So too silly. And then they have a whole category on relativity. Now, why would you do that? I mean, it's just such a waste of. Relativity has nothing to do, the theory of relativity in the absolute sense has nothing to do with the simple observation that yes, you're making relative comparisons. All right, we'll read it for the hell of it. In the 20th century, Newtonian concepts of absolute time and space were challenged by relativity. So again, and in what way defeated? Oh, okay, that's right. No way defeated, of course. Einstein's equivalency principle, which is plainly not very sensible, frankly. I mean, different forces push on you in different ways, and they have hugely different efficiencies. Gravity obviously moves every piece of you equally. It's a force that you could call it atomic, or you could call it nuclear, in the sense that the force is actually moving electrons and protons, and so none of your matter can tell the difference. It can't feel different parts moving at different speeds because it moves every single bit exactly the same speed, and it does it all at the same time. It moves all the pieces at the same time. So there's not like part of you that's being pulled by gravity and then the other part catches up. No, they all move at the same time, relative to our perception, certainly. Other forces have to push on your body, so they push, gravity, your feet get pushed first. So when the earth pushes back, it's not using gravity. It's pushing back with physical matter, and the physical matter contacts your physical matter and pushes it very unevenly. So you can feel the earth pushing you back. You can't feel gravity pushing you in. All right, put all observers moving or accelerating on the same footing. Right, so Newton had a sensible understanding of the universe. It's just this big expanse of space. There's a bunch of distance between material objects. They can crash into each other with momentum and then interact, and it's that simple. And they've turned it all into this wooey mush. This led to an ambiguity as to what exactly is meant by the force of gravity and weight. So obviously there's nothing in doubt about what it's doing. The force is hugely consistent in its function, and weight is easily understood as mass and velocity. Momentum. A scale in an accelerating elevator cannot be distinguished from a scale in a gravitational field. So that's an interesting statement. But it's just that, a statement doesn't mean anything. What does that even mean, a scale? I mean, the scale is not going to move. All right, gravitational force and weight thereby became essentially frame-dependent quantities. I mean, how are you creating any frame-dependent quantity here? Okay, so again, this is relativity. There's no way to make that, what's the point? I put a scale in an elevator. I don't know what the scale is going to just do what a person does. It's going to just go up. You put the scale upside down, I guess. Maybe you could measure the weight, but I don't even understand what they're talking about. This prompted the abandonment of the concept as superfluous in the fundamental sciences such as physics and chemistry. So again, it's superfluous to recognize that there's 3 dimensions of space and everything is traversing in those same 3 dimensions. Okay. Nevertheless, the concept remained important in the teaching of physics. So I don't even know what that means. The ambiguities introduced by relativity led, starting in the 1960s. So yeah, the 60s is where everything went south, I guess. Started to considerable debate among the teaching community again. Again, we have this thing called a teaching community. What the hell is that? Where did the Wikipedia editor interview the teaching community? As how to define weight for their students, choosing between a normal definition of weight, as the force due to gravity. You mean momentum. And yes, momentum's always relative. You can't have any momentum. If we're both sitting on the train, okay, we both have momentum in the same direction, so we can't measure each other's speed because we're both going the same speed. So obviously there's no difference in our momentum. But anytime there's a difference in momentum, that is the vectors of velocity are going to intersect, you're going to have a weight interaction. One is going to be applying weight to the other. Or an operational definition defined by the act of weighing, Well, that was absolutely useless gibberish. Okay, gravitational definition. I don't know if that's very interesting, but let's go for it. Well, the scale stuff. So, yeah, so we'll just do the first bit and see if it goes anywhere. The most common definition of weight found in introductory physics textbooks define weight as the force exerted on a body by gravity, which is true, but any force can duplicate exactly the same function. So any constant force applied to anything that makes it move will make it have weight in the direction of its movement. This is often expressed in the formula W equals mg, where W is the weight. So again, you know, obviously gravity is creating a velocity. So, I mean, if you do mg, weight equals W times mg, you're really just saying without it moving. All right, that's not after it free fell. So, you know, it's not really saying anything. That's saying on the surface of the Earth. That's the only place that's true. Where W is the weight, mass of the object, and G is the gravitational acceleration. So that's only if you're not allowed to move in the gravitational force. There's something stopping you. There has to be a stopping implement force in your way, or that doesn't even say anything at all. All right, 1901, so here's the stupid conference again, the same conference doing the same bullshit, established this as their official definition of weight. So they're doing the same thing again in this web page. They're telling us what some 1901 conference declared the truth to be, and they have to repeat it twice. Oh, it's just so ridiculous. This resolution defines weight as a vector, since force is a vector quantity. However, the textbooks also take weight to be a scalar by defining. So the textbooks do. So you know, they're defying the international standard. You know, the Conference on Weights and Measures. All right, the weight of a body is equal to the magnitude, Fg, of the gravitational force on the body. So again, it's just saying that somehow momentum in gravity we'll call weight, and momentum caused by everything else, we're not going to call it weight. So even though they create weight just as real as gravity creates weight, that is movement of a spring, we're just going to pretend they're somehow fundamentally different when it's fundamentally exactly the same. Weight is just momentum. The gravitational acceleration varies from place to place, sometimes simply taken as a standard value. So all of this little minutia about the fact that you can change it by 3.3%. Oh, crap. Operational definition. Okay, so at least now we have scales here. So the comparison scale is obviously the more ideal scale in the sense that it will always show you, it will measure mass, okay? And the spring scale obviously has the limitation where depending on what gravity, how strong the gravity you're in, you'll get a completely different number. So one of them is immune to the extent of the gravitational force. The gravitational force can be 3 meters per second or 500 meters per second, and the lever scale will get the right answer, where the spring scale gets really confused. All right. And in the operational definition, the weight, it needs to be recalibrated, obviously. Okay, in the operational definition, the weight of an object is the force measured by the operation of weighing it, which is the force it exerts on its support. So it's just the force it supports. So again, they're clearly making a distinction. Force is weight. Weight is momentum. I mean, they're clearly saying it, and yet they deny it. Since W is the downward force on the body by the center of the Earth, and there is no acceleration in the body, well, obviously there is an acceleration. That's the gravity. Fucktard. There exists an opposite and equal force by the support on the body. Also, it is equal to the force exerted by the body on its support, because the action and reaction have the same numerical value in opposite direction. So again, but the Earth can't react until you act first. This can take a considerable difference depending on the details. For example, an object in free fall exerts little, if any, force on its support. So why would they even say these words? So this is a reasonable sentence to you. For example, an object in free fall, we know by idealistic definition, free fall is nothing is in your way. You're in a vacuum and you're falling without anything impeding your capacity to acquire velocity. Exerts little, if any, force on its support. So there's no support if it's free falling, right? I mean, it's just such a bad, stupid sentence. A situation that is commonly referred to as weightlessness. So if there is no support, okay, you cannot be interacting, and therefore you cannot feel any counter force. And again, you can't feel gravity because unlike all the other forces, like even light, right? If I hit you with a laser beam, it doesn't move all your atoms, it disintegrates them, okay, in one place. Now, I suppose if you're even enough with the light and its X-rays, you probably could push something quite evenly. But the point is that gravity is a pushing force on elemental bits, the smallest stuff inside of you, not the biggest. It's not pushing you. It's pushing your atomic bits. They're the things free falling or being moved in the force. They're the ones collecting. They're the sail collecting the wind. However, being in free fall, so you're a bunch of little boats. I shouldn't even have to explain it in those kind of terms, but that's how it works. All right, the real force is being collected, on a material level. However, being in free fall does not affect the weight according to the gravitational definition. So obviously, there's no point in talking about weight as if there's only one velocity for which you can weigh something, and that's the gravitational velocity. So of course it still has momentum. It's just momentum. The word weight ought to just be disposed of, and we ought to just say momentum. Therefore, the operational definition is sometimes redefined by requiring that the object be at rest. Right, and rest in what context? Resting on a surface? Because again, you still have momentum when you're resting on the surface. However, this raises the issue of defining at rest. Yes, of course it would. Usually being at rest with respect to the Earth is implied by using standard gravity, right? So you're obviously constantly pushing into the Earth, and the Earth is constantly pushing you back. In the operational, it's just like you are free falling into the Earth, and the Earth just keeps restoring your position. It keeps pushing you back to where you started from, so you can't gain anything because it just keeps pushing you back to where you started. All right, in the operational definition, the weight of an object at rest on the surface of the Earth is lessened by the effect of the centrifugal force from the Earth's rotation. So there is no force. Your velocity in a direction on the Earth, okay, is not a force out. It's a force to leave the Earth in that direction, okay? And you have to constantly be pushed down. But there is no centrifugal force. The operational definition, as usually given, does not explicitly exclude the effects of buoyancy. So they're talking about centrifugal and buoyancy, in a subject where you're just trying to say what is weight as a concept. And what it is force and pressure and, in fact, momentum, which reduces the measured weight of an object when it is immersed in a fluid such as air or water. As a result, the floating balloon or an object floating in water might be said to have zero weight. So, negative weight, you could say. But obviously, it's a more complex subject, buoyancy, than weight. ISO definition. Oh, I don't know if we want to mess with that. Let's see, where mass is m and g is local acceleration of free fall. So they're doing the same thing. Force equals mg. Now your weight equals mv. Okay. It's just about your velocity. The definition is dependent on the chosen frame of reference. When a chosen frame of co-moving with objects in question, when the definition precisely agrees with the operational definition. if the specified frame is the surface of the Earth, the weight according to ISO and gravitational differs by only centrifugal effects due to rotation of the Earth. So again, just too silly. All right, so apparent, fuck that. Mass, I mean, really, if you have to explain mass to people, you're really in trouble. In modern scientific usage, weight and mass are fundamentally different quantities. Mass is an intrinsic property of matter. So I don't know, there's nothing different between what Newton said and they're going to say here. So it's just bullshit. Whereas weight is a force that results from the action of gravity on the matter. But obviously it can be any force creating velocity. Any force that creates velocity will create weight. It measures how strongly the force of gravity pulls on the matter. So again, it doesn't pull, it pushes. So they can't even get that right. However, in most practical everyday situations, the word weight is used when strictly mass is meant. Yeah, mass moving. For example, most people would say that an object weighs 1 kilogram even though 1 kilogram is a unit of mass. It weighs the same as. I mean, they're making an abbreviation, but clearly they're saying it weighs the same as. The distinction between mass and weight is unimportant for many practical purposes because the strength of gravity does not vary too much over the surface. All right, so there's no point in getting all this minutia about these tiny variances in gravity. The Earth's gravitational field is not uniform. So again, they keep implying that somehow weight isn't this simple idea of what's your velocity. And yes, your velocity changes if the gravitational constant is changed. It's not a big surprise that you weigh a little bit less when you're going a little less fast. And you weigh more when you're going faster. All right, so I mean, too silly. All right, so that's about it, right? There's nothing here. All right, so here we go. Okay, weight is commonly measured using one of two methods, a spring scale or a hydraulic or pneumatic scale. Measures local weight, whatever that is. Relative momentum. Okay, and it's true. It's relative in the sense that you can both be moving this way and then you can measure each other's weight this way on each other, pressure. Since the local force of gravity can vary up to 0.5% at different locations, spring scales will measure slightly different weights for the same object. To standardize weight, scales are always calibrated to read the rate in the object you have in a normal standard gravity. Okay, so you have to adjust your scale, not a big deal. However, this calibration is done at the factory. When the scale is moved to another location, the force of gravity will be different, causing a slight error. So, to be highly accurate, and legal for commerce, springs must be recalibrated at the, there's a little thing on the bottom you can turn. Anyway, balance on the other hand, so balance compares weight compares the weight of an unknown object to one on the scale, pan, to the weight of a standard mass on the other. So yes, you're comparing an unknown to a known. Using a lever mechanism, the lever balance. The standard masses are often referred to not technically as weights, since any variations in gravity will act equally on the unknown and known weights. So yes, it doesn't matter what your gravitational force is because you are going to basically just be comparing two momentums, and the two momentums can't be affected by 10 miles an hour or 20 miles an hour. It doesn't matter. They'll both be affected the same way by the change in gravity, so there won't be any difference in their relative weights. All right, therefore balanced weights are usually calibrated and marked in mass units. So the lever balance measures mass by kind of the Earth's attraction on the unknown and the standard mass. So yes, it's obviously the same force is being applied to two objects, and you're just forcing them to compete with each other, and any differences in the amount of pressure they're applying will be observed. All right, so we're probably way past anything. Yeah, we're already done pretty much. So it's just a crap article. It doesn't really get to the really significant fact that weight is just momentum. Okay. And that weight is just pressure, momentum, and it is energy. And if you compress a scale twice as much, you only have twice the energy. Twice the weight, twice the energy, not 4 times the energy. Okay, the scale does not have 4 times the energy in it because you compressed it twice as much. Twice the weight can't be 4 times the energy because twice the weight can be created by 2 units of energy. 2 units of energy in, you can't make 4 units of energy out. That's free energy. It's nonsense. It doesn't happen. The physics is just so incoherent and sloppy, and it's just junk. It's, you know, flat earthers are liars, but this is as if there were an honest flat earther, this is as dumb as an honest flat earther, which there aren't any of. So I don't know. I can't compare you to something retarded because it's so retarded. Okay, you're embarrassing retards. You're so retarded. You're making retards look awful smart, I guess. Too smart to be this retarded. All right. There's just no point. People. Oh, just... Damn. This is just such garbage. In science, this is the human race's description of reality. It's pathetically silly.